That's us. This is the cover sheet. Okay. What do you want to know about the exam? I was asked earlier. I think I counted correctly. There should only be 2 proofs. Sure. Let's make life relatively easy. I'm going to pick small graphs. So I have, let's see, C3 union P3. Well, the union is just both graphs. That's the union. The sum is the one that connects one to the other. So I have my C3 here on the left, I have my P3 here on the right, and I have to connect each vertex in the C3 to the vertices in the P3. The Cartesian product of the two replaces the vertices of one with copies of the other. There are 2 ways to do this. I could take the P3 and replace each vertex in P3 with a copy of C3 and then connect them like they would be connected in P3. Or I could take each vertex in the triangle and replace it with a copy of a path of 3. Creating a stack of 3 triangles. Both of those are equivalent. This is just turned sideways from this. Better? Oh, you're still looking at it like you don't like it. I draw them both, and then I connect everything in graph 1 to everything in graph 2. So really, that's like K33, but on the one side, I've got a triangle, and on the other side, I've got the path, so it's more complicated than K33. I add in all those bipartite pieces. Well, sure, just add another layer. If it was P4, then I'd have one more. If it was K5, then I'd have stars in each of those spaces instead of triangles. These graphs get really complicated really quickly the more I uglify the pieces I'm using. More questions? Sure. Pick one. We had a whole bunch of them. Tournaments. Chapter 7, right? Yes. Tournaments. If you'll tell me what the problem says, yes. Chapter 7, Section 2, number 10. So 710. Prove that if we have u and v, and the distance from u to v is k, then the n degree of u is bigger than or equal to k minus 1. Idea of u, not v. Okay. The important thing to remember about a tournament is that it is an orientation on a complete graph, right? So the only thing I know about u and v is that they each have total degree n minus 1, where n is the number of vertices. Yes? If the distance from u to v is k, then this is the shortest path to v. Aha. I am 100% sure that there cannot be a direct arc from u to v. Why do I know that's true? That would then be the shortest path. It would be of length 1, and we know the distance is. Can't be a path from u to k minus 1. Sorry, a arc, a single arc. If I did, then I'd have a path of length 2. There can't be a path from u to u2. Sorry, an arc from u to u2. Because if I did, then I could avoid going to u1 and I'd have a shorter path, wouldn't I? Well, there has to be an edge either from u to ui or from ui back to u every time. Because a tournament is an orientation on a complete graph. Yes? If I can't go from u to u2 or u to u3 or u to uk minus 1 or u to uk, then I all have to go the other way. U, ui cannot be an edge of my graph for I equals 2, 3, k minus 1, k. Otherwise, I would have a shorter geodesic. The distance would be less than k. And if UI is not in the edges, then UI comma U must be an arc. How many of those are there? Oh, K minus one of them. 2 to K. So the in degree of U must be at least K minus 1. Advantage. As crazy as it sounds, the only thing I used in this proof is the definition of what a tournament is, the definition of directed distance. Whew. Now, there could be other things pointed at you, but I know there are at least K minus 1 things pointed at you. There we go. And the only one I left out was U1 because I definitely can get from U to U1. That was part of my path. Glad I remembered how to do that.
Like a dominating set to the dominating set, how do we like prove that we know how many there should be in a set besides 5?
Okay, remember that proving that something is a dominating set is just find it, but finding the dominating number is showing that you can't do it with less. Okay, so to find the domination number, you first find a dominating set. So if I suppose that the dominating number of a graph is 3, then I find a set of 3 vertices that works. And then I show that any set of 2 vertices fails. I must show that I can't do it with 2. Most of the time, that's the degree argument, right? That the dominating number must be between 1 plus maximum degree of G and bigger than N over 1 plus maximum degree of G, right? So usually I say, oh, well, if I had a 2 dominating set, then this condition would fail. If I found a 3, so that's good. I can't do it in 2. I need at least 3. Here's a 3 dominating set. It must be the right one. But if you only say, hey, I can do it in 3, then you haven't shown me that you can't do it in less than 3. Same thing with total dominating. Except for the fact that total domination, these 2 criteria don't necessarily hold the same way, right? Because I have to dominate everything else. And that's why the 1 plus has to change. So I need another way to say, hey, if these 2 cover all of these and these 2 cover all of these, then I'm still missing at least that one. And really, most of the time, it comes down to the argument of what are the vertices of highest degree. I think in one of the homework problems, the 2 vertices of highest degree were adjacent to each other. So if I used them both, then I was losing 1 from my count because they had to cover each other. That sort of deal. I find finding dominating number easier than finding total dominating number most of the time. But for the graphs I would ask you to do by hand, it's got to be sitting there in front of me. I can't give you like, here's a 100 vertex graph, find a dominating set. Yeah, right. That could be the whole freaking exam. Here's the matrix for this graph. Draw the picture. No. More questions. Ask me more things. I will tell you that I forgot most of what I put in your exam because I wrote it over Thanksgiving break, and it's been flushed out of my brain by writing other exams in the meanwhile.
So for like Krebs's Russell's algorithm,
Mm-hmm.
both for minimum and treatment differences, hospitals must remain connected to the process.
Well, regardless, since I want a spanning tree, it should be connected at the end.
Yeah.
It needs to be connected and cycle free to be a tree. So yes, I want it to be of lowest weight. Prim's algorithm just goes in order from lowest to highest weight and just adds, as long as I'm not making a cycle, I'm good. Kruskal requires me to pick some place to start and only add things that are lowest that are still connected to those. Again, without making a cycle at any step. Now that I've said that, I think I said that exactly backwards. Kruskal's is the one that just builds. Prim's stays connected. Because Prim's is the one where we do the matrix version, and that's why it stays connected, because we're always going to a row we've already started. Yes, yes. So the reason for doing the matrix version is because it keeps track of what's already been moved into the set of vertices I'm allowed to look at. We did Kruskal first and Prim second. It turns out there are other minimum spanning tree algorithms that are variations on all of those, but those are the most easily coded and most effective at this point. I mean, we can improve accuracy if we know more about improve the algorithmic efficiency. If we know more about the graph, if we know how connected it is or how sparse it is, it might be easier to do the matrix version of Prim's because there'll be a lot of zeros in there if it's a fairly sparse matrix. That's connected and related to Dijkstra and Floyd-Warshall in terms of, oh, you got to build the matrix first. Oh, and someone pointed out to me a version of the Floyd-Warshall algorithm online that actually lets you draw the picture, and it will create the matrix from the picture. You have to draw the picture, label all the vertices, and then weight all the edges, and then it will construct the matrix and do Floyd-Warshall. I was impressed as hell. I think it had a maximum depth of 12 vertices. Because the drawing part became too unwieldy to handle at that point. It became one of the higher ranked results on the Google search, like third or fourth. Yes, ma'am.
Can you do a question like, 12.226, we have to find the peripheral, eccentric, and boundary vertices?
Okay. Need another example. Would be one from. I have one in this book. Boundaries of faces. No, that's about planarity. I'll make up a graph and we'll hope it works. Let's do a smaller version of what's in that problem. So I'm going to go ahead and take square with a single diagonal, another square, and then a square with the opposing diagonal. Okay. Definitions. In order, I go from peripheral to eccentric to boundary. Every peripheral vertex is an eccentric vertex. Every eccentric vertex is a boundary vertex. So the first thing I need are the eccentricities of all of these. What are the eccentricities? The vertex furthest away from A are vertices D, G, and H. All of those are distance 3. 1, 2, 3. So the eccentricity of A is 3. The eccentricity of B is 2. It's 1 step to A, E, F, and C, and then it's 2 steps to D, H, and G. Okay, well, then by symmetry, the eccentricity of D and C is also 3 and 2 respectively, because it's the same picture in both directions. How about E? What's the eccentricity of E? Well, then I'm going to say that H is also 3. What about F and G? Because from F, I can get to B, E, wait a minute, it's 3. I get to B, E, and G in 1, and get to A and C and H, but to get to D, I got to do 3 steps. Oh, okay. Well, all right then. The periphery is the set of vertices of maximum eccentricity. So that's everything except B and C. Okay. A vertex is eccentric if so I need you to find me a vertex on the graph whose distance is matching the eccentricity. Well, for here, I know it's the vertices that are furthest away, right? So there's no question I can do it for those. Can you find a vertex whose distance from B is 2? Yeah. 1, 2, 3. All have distance 2. How about C? That's the problem. These vertices here, D, G, and H, are eccentric of B. But our goal is to go the other way and show that B is eccentric of something. So, is there any vertex here whose distance to B matches the eccentricity of that vertex? No. Because the distance from C to B is 1, and the distance from all of these to B is less than 3, because the distance from B to anything is a maximum. So are those eccentric vertices? No. Which means the set of peripheral vertices is the same as the set of eccentric vertices. What makes a vertex a boundary vertex? This is why you get a formula sheet. Write down definitions like this. Vertex is a boundary vertex of something else. So A is a boundary vertex of another vertex if the distance from that other vertex to A is bigger than or equal to the distance to all of the neighbors of. So pick a vertex. Now, peripheral vertices are eccentric vertices are boundary vertices. So if I start at A, the distance from H to A is 3. The distance from H to B or E is less than that. Yes? So A is boundary of H. The only two things I have questions about are these two. Is B a boundary of some other vertex? Let's start at F. The distance from F to B is 1. I'm in trouble. Is the distance to any of the neighbors smaller than that? So let's move further away. The distance from G to B is 2. Is the distance to any neighbor of B less than or equal to 2? Distance from G to A is 3. That's bigger, not smaller. So B is not a boundary to G. It's not a boundary to E because the distance is 1. So 1, 1, 1. Those are definitely out. 1, 1. 2. We just decided that one was out. The distance from D to B is 2. Is there a neighbor of B whose distance is further away? Yes. The distance from H to B is 2. Is there a neighbor whose distance to H is further away? Yes. B is not part of the boundary. Symmetrically, neither is C. So the set of boundary vertices is also the same set. So really, it's measuring how do I get there from here? And the answer was, I couldn't get there the right number of steps. So it as the furthest away thing. I couldn't make B the furthest possible thing from something. No matter what I did, when I tried to go to B, there was something on the other side. Better? To be not part of the boundary. So I said, can you get something where B is as far away as you can get? That would put it on the boundary of my reach from that spot, right? But it turns out no matter where I am standing, there's always something further away.
You said like every peripheral vertex is a boundary.
Bottom of page 336. Every peripheral vertex is eccentric. Every eccentric is boundary, but boundary may not be eccentric. Eccentric may not be peripheral. Yes. If it's peripheral, then it's eccentric. If it's eccentric, then it's boundary. Exactly. Because now I know once you're in the periphery, you're automatically in the eccentric, you're automatically in the boundary. I only have to check the others. And that's why I was only looking at B and C all this time, because I knew I got the rest of them for free. Again, I'm going to go right to the definition. A vertex is eccentric if I can find a vertex V such that the distance to U is the eccentricity of U. So find a vertex whose distance to B is the eccentricity of that vertex. Not the eccentricity of B, but the eccentricity of where we started. So in that case, I would need something whose distance from B is either 2 or 3. Is the distance from C to B 2? No. Is the distance from any of these to B 3? Then it's not eccentric. To any of them. Of. Got to use the right preposition, Jonah. The eccentric of any of them. Well, but the interior is just the set of non-periphery, right? I'm sorry, that's the center. Never mind. Apologize. The interior vertices.
There's one
Between two others, yes. And in a sense, interior and boundary are kind of opposite here. There's no question B is interior of A and C, right? Hard to put it on the boundary then. That certainly does help. Again, if I would need another definition for me to jam into my brain, and I had forgotten all about that when I was just going off the definitions from these. There is an awful lot of crossover between what we do here in finite measurements, integer measurements between objects, right? And what we do in analysis, where we're measuring distance continuously. I draw little circles of radius epsilon to talk about continuity all the damn time, right? 207 is a pain in the ass, but that's where it starts. It starts with the idea of how close things are, how measurable they are in distance. This is the discrete version of that. And in one sense, graph theory is analysis without ever needing epsilons and deltas. So boundary and interior and periphery and eccentric and center are parallel ideas to a little disk being on the edge of that disk, being outside, being inside. Topological ideas that we use in analysis, like we do in Calc 3, where we talk about the boundary of a region. Or Calc 1, where we talk about taking an integral and then only looking at the ends, the boundary of that section. We do all this in the same way. But this sounded like nothing we'd ever seen before, right? It is the same stuff, we just hide it really well. I sent you all on Tuesday last week a copy of my final exams, hours and such. This exam is like 1 o'clock. I'll be in the enrichment center before this because I have another exam for 8 to 10. For those of you in the abstract course, I apologize. I didn't make up the schedule. Both the exams are on the same day. All right. If you've got questions, come bug me. Otherwise, I will see you all tomorrow. Have a wonderful rest of your day. Congratulations. You made it. Nobody's exploded yet.